Generalized Biot-Savart law. The law of Biot and Savart, B is equal to mu 0 over 4 pi q v cross r hat over r square, generalizes to the case of surface currents as mu 0 over 4 pi integral sigma v cross with r hat over r square dA, where sigma is the local charge density, v is the local velocity, and dA is a differential area element. Revisit problem 28.76 and use the above equation as an alternative means to derive the magnetic field at the center of the cylinder, and use the following steps. Part A, write the charge density sigma. Now for this cylindrical shell, the surface area is 2 pi capital R multiplied with W. So for uniform charge distribution, our surface charge density sigma can be written as the total charge it carries, Q, divided by the area, surface area, which is equal to Q divided by 2 pi R, 2 pi capital R, W. So this is our surface charge density that we're supposed to find in part A. Part B, the origin is at the center of the cylinder. What is the vector R that points from the element with coordinates x, y, z, x, r cosine phi, r sine phi, to the origin? Okay, so we have a point here which is x. On the x-axis, it's at point x. It has an y component r cosine phi and z component r sine phi. Now you can see that in this case phi is on the yz axis. So that's the azimuthal angle, which is defined on the yz axis with respect to the positive y-axis. So this vector r points from this element to the origin. So r points from x, the y component is r cosine phi, z component is r sine phi, to the origin, which is 0, 0, 0. So we can write the r vector as 0 minus x I hat plus 0 minus r cosine phi j hat plus 0 minus r sine phi k hat. So that's how we can write this position vector. So let's write the final answer for the position vector. Position vector r is equal to minus x I hat plus r cosine phi j hat plus r sine phi k hat. This is the position vector of the element at this location. What is the velocity v of that element? Okay, so this is basically rotating in the counterclockwise sense, looking from the top. So I can see that this element is moving with tangential velocity v in this direction. So that v vector is on the yz plane. So that's the first thing I note. V is in the yz plane. So the x component of the velocity is 0. And it's performing uniform circular motion. So the tangential speed v is related to its angular speed, capital R times omega. And if I look at this velocity vector on the yz plane, you can see this is counterclockwise sense in the yz plane. This is my velocity vector. Once again, r cosine phi j hat, r sine phi k hat, no x component. I can write the velocity vector as 0 I hat, and then I will have v cosine phi So if I write its y component, it will be v cosine phi j hat, and it's because this is the velocity vector here, not this vector, so we have to be careful. This is a right triangle. This is 90 degrees, 90 minus phi, phi. So v cosine phi is the z component, and v sine phi is going to give me the y component, but it's pointing in the negative direction. So being careful with this angle here, this is the vector whose projection onto yz axis we're trying to find. We can write this velocity vector as v is equal to minus v sine phi j hat plus v cosine phi k hat. So v, the speed, is basically r times omega. So this is minus r omega sine phi j hat plus r omega cosine phi k hat. So that's the velocity of that element. Now in the Biot-Savart law, we have v cross product with r hat, so we need to find that cross product. Now that we have written the two vectors, v cross product with r hat is actually v cross product with r vector divided by the magnitude of r. R vector divided by the magnitude of r is the unit vector pointing in that direction. So what is r here? R, the magnitude of this position vector r. So for this position vector r, we have square root of capital R square plus x square. So you can see this right triangle here. So this is capital R square plus x square is equal to r square. All right, so that will give me, for the magnitude of r, capital R square plus x square square root. Now let's do the cross product. This will be minus r omega sine phi j hat plus r omega cosine phi k hat. That's the velocity vector. Cross product with r vector. So let's move this here. Cross product with r vector, which is minus x I hat minus r cosine phi j hat minus r sine phi k hat, and all of this will be divided by the magnitude of r, 1 over r. Okay, so let's start doing this cross product. R omega sine phi j hat cross I hat, but with a minus sign. So minus sign j hat cross minus sign j hat cross with minus sign I hat, minuses cancel. So I obtain j hat cross with I hat, j hat cross with I hat, that's the negative direction, minus k hat. So this gives me minus r omega x sine phi k hat. That's the first term. And then I have the second term. The second term is minus j hat cross with minus j hat, which will give me 0. J hat cross j hat is 0. The third term is minus j hat cross with minus k hat. So that's j hat cross k hat. J hat cross k hat is I hat from the cyclic permutations. So I will obtain for this, r square omega sine square phi I hat. So this is plus r square omega sine square phi in I hat direction. Now for this term, k hat cross with minus I hat, that will be I hat cross k hat. So I hat cross k hat is basically minus j hat. So this term gives me minus r, capital R omega x cosine phi j hat. And then I have k hat cross with minus j hat, which is j hat cross k hat. J hat cross k hat is I hat. So this will give us plus r square omega cosine square phi I hat, and all of this will be divided by r. So if I work on this, let's look at the I hat components. R square omega sine square phi and r square omega cosine square phi. Sine square plus cosine square is 1. So the first term here is omega r square in I hat direction. Then for the j hat components, I have minus omega r x cosine phi j hat. That's the only component here. So minus omega capital R x cosine phi j hat. And for the k hat component, we have minus r omega x sine phi k hat. So we will have minus omega r x sine phi k hat, and all of this will be divided by r, magnitude of the r vector. So putting the magnitude of the r vector, square root of r square plus x square. Well, you can also see that here, square root of r square cosine square plus r square sine square, that's r square plus x square. That's the magnitude. We will write v cross r hat, final answer for this part. Now we have r omega divided by x square plus r square square root. And the first term here was omega r square I hat, so omega r parentheses, that will give me r I hat. And then for the other two terms, I have a common x, so minus x r omega parentheses, so I obtain cosine phi and sine phi. So this is going to be minus x cosine phi j hat plus sine phi k hat. So this is the final answer for v cross r hat. That's the answer to part D of the problem. We will work on the parts E and F in the next video. So for now, let's see what we did. First, we found the surface charge density Q over the area A, which is Q over 2 pi rw. Then we have written the position vector of the element at location xr cosine phi r sine phi, so that the phi is the azimuthal angle on the yz axis with respect to the plus y axis. It points from this point to point 0, 0, 0. The velocity vector, the tangential velocity vector, you can see if you look from the top, if this is rotating with angular speed omega, this is a tangential velocity in this direction, which is in this direction, and that angle phi defined with respect to the positive y-axis is here, and the positive z-axis is here. So this is my tangential velocity vector, which makes an angle phi with respect to the z-axis. So its z component is its magnitude times cosine phi. Its y component is its magnitude times sine phi with a minus sign because it's pointing in minus j hat direction. And when I take the cross product v cross r hat, I have to find the magnitude of vector r, which is square root of r squared plus x squared. Then I carefully take the cross product, considering these two vector components, and finally divide it by this r here to get the v cross r hat vector product, and that's basically the final answer I obtain. So I'm going to use this answer in the modified Biot-Savart law in order to calculate the magnetic field at the center.